afternoon, everyone. It's wonderful to have you here. Many of you have been here for the last 2 days. We've had this AI and economic history workshop. Learned a lot. There's also clearly still a lot of work to be done and a lot of excitement about the future directions of the field. And part of organizing this workshop was that I wanted to invite people that are doing really interesting things. Many of you presented, and I thank you for being here. But there's also a paper that was really standing out to me, and this was the paper that Meredith Baker was part of, or is part of, and that she will talk about today. And this is really kind of not only looking kind of forecasting into the future, but also thinking about gaps in the data in the past and how we might use these new tools to fill in the gaps. So let me just say very briefly something about Meredith. Meredith is assistant professor at Grinnell College. She received a BA in economics from the University of Georgia and an MPhil and PhD in economic history from Oxford, where she was a Marshall Scholar. And Meredith's research and teaching areas are economic history, of course, but labor economics as well, and econometrics. Research focuses on unemployment, structural change, inequality, and employment practices in historical labor markets. Research has been published in top economic history journals, including the Journal of Economic History, the Economic History Review, and Explorations. And she's previously worked as an economist at the Federal Housing Finance Agency. Meredith, thank you for accepting the invitation. I should also add that Meredith is joining Oxford again from next year on. So it's nice to also involve those links, and congratulations on that appointment. But we really look forward to what you have to share with us on understanding and predicting the box. Thanks.
Thank you so much. And can everyone hear me okay? Great. And I am just so delighted to be here. Stellenbosch is such a beautiful place, and I really appreciate you coming to this talk. I heard there's a Nobel laureate also giving a talk this evening, so thank you for choosing this one. I wanted to start today with this Pew survey, which asked people in 25 different countries if they were more excited about AI or more concerned about it. And across almost all countries, people reported that they were much more concerned about AI than they were excited. At the median, 34% of people said they were concerned, and only 16% said they were excited. And while, of course, there's variation across countries, this really sparked my interest, because where is all of this concern coming from? And I think it's coming from the fact that AI hasn't always delivered what it's promised. Systems and tools that were supposed to make life better have had unintended and sometimes even harmful consequences. And so I just want to talk through a few examples of this. So first, let's think about Netflix. In 2006, Netflix posed a $1 million Netflix Prize problem to computer scientists, and they asked them to develop an algorithm to help people to select films that they would like based on the films they'd already watched. And they conducted this, recommender systems were developed, but then these same algorithms are the same ones being used by TikTok and YouTube. And we're increasingly learning that these have led to decreased attention spans, radicalization, and rabbit holes that some of these documentaries cover. As another example, think about autonomous AI and computer vision. We were promised to have mass-scale self-driving cars to make the roads safer and our commutes more enjoyable. But exactly these same innovations are those that have been used to make autonomous weapons, which can identify and kill human targets without any involvement from a person. And so this led to this New York Times article, AI begins ushering in the age of killer robots, which sounds like something science fiction has always worried about. Think about Google search, which I think is one of the greatest innovations of our time. It's put all of the world at our fingertips. But that same goal to rank and retrieve information with AI has led to this little box that now appears when you search things on Google. And this little box can be very misleading. So in this example, you Google search how to prevent cheese from sliding off of my pizza, and the AI is saying just mix in 1/8 cup of non-toxic glue like Elmer's school glue into the sauce to add tackiness. And then lastly, think about large language models and ChatGPT. ChatGPT says it's here to help. It's always saying, how can I help, Meredith? But increasingly, workers find that they're being replaced or laid off as businesses try with varying degrees of success to replace them with tools like ChatGPT. And the consequence of these developments have led some to gain riches and to potential environmental costs. So this is the stock price of NVIDIA, which makes the chips for AI processing. And you can see it's going up and up. And I should have put a new screenshot because it's the first stock to break $3 trillion, $5 trillion, thank you, which is, I mean, amazing, insane. In the center here, you have Sam Altman, who's the CEO of OpenAI, which makes ChatGPT. And he was invited to Windsor Castle to meet with the royal family as part of Trump's 2025 September state visit to the UK. And then this is just one of many articles that you can find about how the resource demands of these new tools have environmental costs. And so there are a lot of reasons that people are feeling concerned. But today I wanted to ask a different question. What if we use AI differently? These techniques are not just useful to predict or influence what we buy in the future or to drive our cars. I want to talk about how we can use AI to look backwards, not forwards, to help us answer stubborn questions in history that we otherwise weren't able to answer, and to uncover these patterns in historical data that have been difficult to process at scale. And so my hope is that this will give us at least one reason to be excited about AI as we go into 2026, more so than concerned. So what I'm going to do today is first, I'll briefly introduce machine learning so that we're all kind of in the same space. And then I'll talk about some of the ways that machine learning has been used in previous historical research. But most of the time, I'm going to talk about this paper, Predictive Modeling the Past, which I wrote with Patrick Wallace at the LSE and Judy Stevenson at UCL. And this method, called past predictive modeling, is a way to use AI to address one of the most pernicious problems in economic history, which is that as we go further back in time, there's less and less data. But first, we're going to start with a quick introduction to machine learning. So we're going to start with some common definitions from textbooks. And so I want to start with the Murphy definition. The goal of machine learning is to develop methods that can automatically detect patterns in data, and then to use the uncovered patterns to predict future data or other outcomes of interest. So from this definition, we can see that data is key to machine learning. We need this data in order to detect patterns. But we also see that prediction is a core idea. How can we use these data to make predictions? And the Mitchell definition is capturing a similar concept, but is introducing letter notation. So a computer program is said to learn from experience E with respect to some class of tasks T and a performance measure P if its performance at task T as measured by P improves with experience E. And so you can see why machine learning is sometimes hard to understand. But what we can glean from this definition is that prediction is just some kind of task. And we're going to measure how well we did at this task with some sort of performance metric. And the idea of machine learning implies that there's a process by which we can get better and better at doing this task, improving with experience. So what we can take away from these definitions is the observation that a machine learning problem is always specific, well-defined, and bounded. We have a clear goal or outcome. We're using measurable inputs and outputs, and we're going to evaluate our performance quantitatively. And our data is always finite. We have clear limits on the scope of the kind of questions that we're asking. And so it's important to remember that we're not Dr. Frankenstein building some sort of artificially intelligent monster machine here. We are specifying and solving a very specific kind of mathematical, statistical problem. And then as we talk about machine learning, I also just want to quickly address our nomenclature. AI, which stands for artificial intelligence, encompasses more than just machine learning. And right now it's often being used equivalently with like ChatGPT or large language models. But almost all AI is machine learning because computers are processing things faster than humans. And as a type of AI, all machine learning is also AI. And so because I'm kind of grounding our understanding here in optimization, and we're thinking about optimizing the performance of tasks, predicting an outcome, I'm usually going to describe things as machine learning. So usually we think about 3 types of settings for machine learning problems. Supervised learning is the bread and butter of the kinds of questions that we usually ask as economists. This is when we have data with inputs and outputs, like variables and outcomes, and our goal is to create some kind of mapping from those inputs to outputs. Unsupervised learning involves data that we use a lot less in economics, where we have a bunch of inputs, but no information on the outcomes. And the goal here is to find patterns or hidden structures in the data. And then reinforcement learning is like training a dog. So you'll use trial and error, rewards and punishment to try to generate a good result. And so this requires data on the interaction of an agent with an environment. And the choice, there is a choice that's made, and then you're going to see what happens next. And it's important to note that these aren't siloed off from each other. There's a lot of approaches right now that are between supervised and unsupervised learning, blending a bit of both, like self-supervised learning and semi-supervised learning. And so if this was too much for you, I think of this in my head like cooking. So in supervised learning, you're following a recipe. You know what you want to make, what ingredients you need, the output you're trying to get, and you reproduce that output. Unsupervised learning is when you forgot to plan your meals for the week. So you open the pantry and you see what you can create from whatever is on hand. You're experimenting with new flavors to see what goes well together. And then reinforcement learning is like when you have a picky child and you're trying to learn what they like to eat. And so you'll just give them things and adjust based on their feedback, see what causes the least amount of tears. So within each of these broad types of machine learning, we usually break these down into different kinds of tasks and problems. Under supervised learning, we are mapping inputs to outputs. If we're predicting categorical outputs, meaning different categories of things, that's called classification. And if our outputs are numbers, that's called regression. And so these are like the recommender systems that I mentioned at the beginning: Netflix, YouTube, TikTok, and also Google page ranking, though nowadays that's using some other stuff as well. Unsupervised learning is usually divided first into clustering. So there, our goal is to group similar things together, or into dimensionality reduction problems, where we have some high dimensional data that we want to represent with lower dimensions. And then I've put self-supervised learning in this category, even though it's really bridging both supervised and unsupervised learning. And this is when missing labels are predicted from raw text. And so this is like ChatGPT and generative AI predicting what word can I say next that will give you an answer that sounds smart and reassuring. And then reinforcement learning is really about this sequential decision making. So you're learning what works best in an environment. And so this is used in autonomous vehicles as they decide how long to wait at an intersection. And so the idea is that as they drive more in a specific city, they're supposed to get better and better at driving. So some of you might be thinking now, couldn't we already make predictions without machine learning? And especially in this area of supervised learning, where we're mapping inputs to outputs. Don't we already know how to do that, thanks to introductory statistics? And indeed, linear regression, or ordinary least squares, is kind of like the original supervised learning problem, where we're trying to make a prediction. And so with data, we have data that has inputs and outputs, and we usually call these x's and y's. And we're going to find these betas that are minimizing the sum of squared residuals to prove that we can prove that under certain conditions, these are the best linear unbiased estimates. So in this little equation I've written up there, beta 1 is quite literally mapping how changes in our input x are affecting our output y. And so then once we have beta 0 and beta 1, we can make a prediction for y from any kind of set of x's. But in the case where we're focused on making a good prediction, machine learning is usually improving on these traditional regression methods from econometrics. So usually in a regression, our goal is to get an unbiased estimate of beta 1. This is going to tell us how x and y are related. And under certain conditions, we can say this is a causal relationship. And that's what a lot of economics is still all about. And regression models are still very good at causal inference, generating these unbiased and stable coefficients, and they're used in a lot of econ, though much more complicated than the one I have up there. But the observation is that technically we don't need to understand this relationship between x and y parametrically in order to get a good prediction of y. If all we care about is that prediction y, which is how our machine learning question is framed, remember we're just interested in predicting our task, then regression models can be beat by algorithms that are prioritizing predictive power, such as gradient-boosted decision trees and neural networks. So why are these machine learning algorithms so powerful? In general, this is because they're more flexible. So instead of having to specify all of the nonlinearities and complexities, these are determined almost automatically. And this flexibility better models complex real-world relationships that might change over time or be caused by multiple factors. And all of this flexibility is often balanced by regularization, which ensures that our prediction is going to work well in new, unseen settings. And so the combination of these traits makes machine learning algorithms very good at making accurate predictions in complicated and dynamic systems. So now let's talk about how machine learning has been used in economics and history. My view is that machine learning has already transformed economic research. It has become a standard technique that people draw on in cases where they're trying to make a prediction. It's been shown to outperform OLS, by which I mean linear regressions, in terms of predictive power in cases like predicting house prices, forecasting GDP, predicting recessions, demand estimation. And this Kleinberg et al. Paper describes a broad set of what they call prediction policy problems where machine learning prediction methods might be helpful. And so some of these questions that economists are interested in predicting are things like, was someone hired or not? Will a defendant appear for a trial or won't they? Is this loan going to default or will it prepay? And research by Goulet-Coulomb et al. Has shown that the reason that these machine learning models are doing better than regression models is that it's their increased flexibility. And so machine learning is increasingly becoming kind of a best practice in econ when our goal is to predict something. What about in history? So I think machine learning is on its way to transforming history, but most of our use cases so far have been in gathering and processing data. And we're going to talk about these 4 examples in more detail here. Digitizing historical data, extracting data from complex historical sources, natural language processing, and linking individuals across censuses over time. And these aren't the only cases, and we've heard wonderful work in all of these and other areas in the past few days, but these are the ones that I wrote slides on. So the classic example of early AI and machine learning for history is OCR, optical character recognition. And this can take text from historical and modern day documents that are printed and increasingly handwritten and convert it to digital. And so in that taxonomy of machine learning that we went over, we can think of this as a supervised learning classification problem. We're going to take these pixels that you see on the screen, and we're going to classify them into numbers or letters. And so this is a picture from a subset of the MNIST data, which was originally used to train OCRs and now is used in a lot of other settings. So this used to be harder to do, but nowadays you can easily OCR. My phone can OCR things, but you can also use one of Tesseract, Abby Fine Reader. You can pick your favorite tech company, Google, Microsoft, or Amazon, and they all have OCRs. In history, OCR is especially important for scale. So as economic historians, we've always been happy to find archival data and type it into Excel. But that is literally impossible for sources that are hundreds or thousands of pages. So for example, in my work on the 1920s and 1930s in Britain, I used OCR to digitize hundreds of pages of these tables of employment data that are archival data. And I basically took it from photos, like the one that you see on the right, and converted it into an Excel spreadsheet on the left that then I could put into statistical software. And so data digitization will probably continue to be the #1 way that historians are using machine learning. Our second example is using machine learning to extract content from complex document layouts. So historical sources often have complicated formats that can lead to really messy OCR output if you just throw it into Tesseract. Machine learning can help us to extract the content from the pictures of these sources by analyzing their layout. And so here the goal is to detect where are titles and sections and headings. And this is a form of supervised learning. So you need to have training data that does this kind of detection that then you can use in new settings. For example, here are some images from a data set of documents from 1950s Japan in a working paper from Shen, Zhang, and Dell. And you can see that machine learning is used to detect the titles and the sections. And this shows that this is really valuable, especially with Asian sources that have these difficult and different kind of layouts than we're used to. This can also help us with newspapers, where we want to keep articles separate, but they're in these tiny columns all over the page, broken up by images. Melissa Dell and many co-authors have developed a data set of over 1 billion content regions from public domain US historical newspapers, and have used supervised learning based on these data to extract content layouts. And then you can use their model to extract the layouts from new sources. And so this is kind of a very another very active area of research using machine learning to extract the layouts from complicated content. A third example is natural language processing. This is where topics, sentiments, and other data can be extracted from raw historical text. Topic modeling, which is one kind of natural language processing, is a classic example of unsupervised learning, where words are grouped together to identify key themes. So, for example, this 2017 paper by Hansen, McMahon, and Pratt in the QJE conducts a topic modeling of the transcripts of FOMC deliberations from 1987 to just after the Great Recession. And what they find is that right before a recession, monetary policymakers suddenly start shifting their discussions from growth towards questions of economic weakness. And so they argue that this can be an early indicator of recessions. These kinds of analyses have been used to study central bank and political discussions across many countries, and we have lots of this text as data that can be used and analyzed with increasingly better and better natural language processing methods. And then my final example is record linking across censuses. And this has been a huge area of work in economic history. The idea here is that we want to be able to track individuals over time through often decennial censuses. We have all of this information in every census about an individual's birthplace, their age, their family, their neighbors, sometimes even their job. Can we find that same individual in the next census? And this isn't as easy as it sounds because US censuses, they don't record some sort of government identifier, and there are a lot of common last names like Smith or Kim, and because there are cultural norms where people change their names at certain life stages, like women getting married and changing their last name. So originally this was done with rule-based and probabilistic, non-machine learning methods. But now that it's almost entirely done only with machine learning methods that are going to take all available data and use supervised machine learning models to determine if two individuals are a match or not a match. And so in the US, you can now download multiple historical censuses with a generated ID that will link individuals to the extent possible over time. So this is a photo of a website called IPUMS, which is a website that anyone can go to get US Census data. And you can just download the 1850 and the 1860 censuses, 8 million cases where people were matched over time. And this is also an area where the methodology is another active area of work. So at this conference, we heard about the census tree, which is a strategy to combine links from multiple machine learning models to get the best possible links. And so this is going to become the newest and largest database of US Census links. We just heard they're matching like 70% of people on average. This is all based on genealogical data collected in Family Search. And so they're going to make new links from this data using supervised machine learning, which you can see there. And then they're also combining this with all other existing links from supervised and unsupervised models, including the MLP links, which are the ones that you could download on IPUMS on the previous page. So it's very exciting. So to summarize, these are all exciting applications of ML to history: digitizing new data, working with complex data layouts, natural language processing, and record linkage. But there is a pretty clear gap here. All of these applications relate to the gathering and the preparation of data that's then used in other analyses. We get this linked census data set. We can follow Jane Doe throughout all of the US historical censuses, but then our next step is to run a least squares regression to ask an economic question. Remembering that the core strength of machine learning is prediction, and economists are using it to predict real things like GDP and house prices, and as a go-to method for prediction policy problems, we have a missed opportunity here. When we only use machine learning to prepare historical data, and then we switch to traditional methods to analyze that data. And so this raises kind of the fundamental question: what if we use machine learning to actually understand economic outcomes in the past instead of just to develop new sources? And this is kind of the frontier that we are trying to explore, and that I'm going to talk about today, using machine learning for historical analysis and not just data processing. And so to do this, we're going to get much more specific talking about this. This paper with Judy and Patrick called Predictive Modeling the Past. And this is a working paper that we, and set of code that we released in June. And so how this relates to everything that we've talked about so far is pretty simple. We're going to take a prediction task, something that we've always done with ordinary least squares regression, and we're going to replace that with powerful machine learning algorithms. And then we're going to ask two questions. First, is this methodological improvement actually causing our predictions to be better, more accurate, and more precise? And then more importantly, do these improvements lead to new historical knowledge? And so this is where we're heading, but I need to provide you like a little bit more context in order to understand the context in which this prediction is happening in economic history and why the new approach matters. So, predictive modeling the past. So we're going to start with the problem of scarce data in history. Some people describe today as an age of big data, and I think it's possible Amazon knows more about me than I do myself. But if today is the age of big data, history is the age of small data, and increasingly small data as we go further back in time. And this is not monotonic, but the amount of data that was collected and preserved does generally decrease the further back that we go. This is an increasingly important problem because as a field, we're more and more interested in questions that relate to what I would call the very long run, trends over hundreds of years. So examples of some of these questions, we might ask, how much better off are we than we were 700 years ago? How did COVID-19 compare to the Black Death? Why did some countries break free from poverty and destitution before others? These all require very long run data sets. So the fact that our data are generally scarce as we go back in history is a huge challenge in our ability to do this. We have to use some technique to take all of this fragmentary, scarce historical data and derive what we need, which is a long-run time series from these data. So to illustrate this problem of data scarcity, take, for example, the number of observations we have of wages that were paid to laborers in England. This represents the largest collection of historical wage observations that we know about. And conveniently, it is also the data that we're going to use to validate our model later on. And so we have over 9,000 observations of wages that were paid to laborers at different sites in England. And these were all building sites. So these are, you can think of the laborers are doing tasks like digging ditches. And so we have 9,500 observations. If you're a historian, this sounds like a lot. But over the course of 7 centuries, this should give us around 136 observations per decade. The issue is that the data are unevenly distributed. The 1890s have over 900 of our observations. And in the 1240s, we have exactly 3 observations. Data is especially scarce in some periods that are periods that we are very interested in historically, like after the Black Death and in the mid-15th century. And so on average, there are only 13 observations of laborers' wages in every year. And so if you look around, that's less than the number of people in this room to represent an average wage in an entire country for a year. We are looking at English wages because these are the best available data. But in the paper, we take the time to survey work on other countries and different time periods to see if this is kind of a general problem. And some of that work is summarized here in this table. And so you can see in all cases, data scarcity is a serious problem. If you look at this last column, observations per year, it's rare to have more than 50 or 100 observations in every year. And this problem is going to become more serious when we start putting these wages in regression models that have a lot of parameters in our quest to generate sort of a long run series. And I should emphasize these papers are on different countries. Some of them are on England, but some of them are on Italy, Japan, etc. So I've been talking about generating this long run series of wages, but as a quick refresher, I want to talk about why we want a long run representative series of wages for a country anyways. Why is this a good goal? And the answer is that wages are our key measure of standards of living over time, and they're a proxy kind of for economic growth. Wages were paid in most countries, and most countries had people doing a task kind of like a laborer. And so if we can compare how much laborers were paid in different countries, we can understand differences in prosperity between these countries. So for example, this is a comparison of wages in key cities from 1738 to 1918 over time, scaled by a cost of living measure, which you don't need to worry too much about. But this is kind of an example of how one of our goals in economic history is to be able to make these comparisons, looking at the long run to see, like from this you could draw the conclusion that London is diverging from Amsterdam in the early 1800s. So this is what we want to use the wages for. But back to our problem, we have very few observations in every year. And if we don't have a lot of data, and the data we do have is coming from diverse sources, maybe from different areas of a country, how can we determine which wage should go in this graph? And the solution, pioneered by Bob Margo and Gregory Clark, has always been to use a least squared regression model. A regression can control for observable factors that might influence wage levels. So it's kind of standardizing the wages across the nation to predict a national wage estimate in every year. So for example, this is the regression used for craftsman wages in Clark's 2005 paper. We don't need to fully unpack this if this is scary. But the thing to notice here is that we're controlling for the type of craft, meaning if you're a carpenter, a roofer, a plasterer, the town, the region, and the year. And the big thing is that we're going to run this one single model on all 700 years of data. And so this is the kind of regression that's used in all of these papers, though of course they have differences in exactly how it's specified. And I should also mention that these regressions are not just used to generate time series of wages, but also to generate time series of other measures that are interesting to economists, such as agricultural productivity and prices. So regressions like these have been the standard for 20 years, and they've been used in economic history to solve this problem of representativeness, uniting data from diverse sources to predict this sort of nationally representative long-run wage estimate. But as we've learned, we took the time to remind ourselves machine learning can help us with prediction problems, and it offers these advantages over standard regressions. And so the big idea of this paper is to use machine learning and predictive modeling techniques to improve the generation of these long-run representative wage estimates. And so the focus of our paper is on introducing this new method that we call past predictive modeling. This is going to leverage machine learning and predictive modeling to solve this problem of reconstructing the long-run time series of wages. And so we're going to take techniques from predictive modeling, forward predictive modeling, like what's currently happening now in finance, and we're going to focus on how well we can build models that are predicting backwards in time. So we'll be using the more recent data to make predictions of past values. And then throughout, we'll be optimizing on out-of-sample predictive accuracy to ensure these are representative estimates. And then we'll also advance the method of prediction. So instead of using a regression, we're going to use these machine learning algorithms. So before we dig into this, I want to be a little bit more specific on what exactly we can improve on using this new method. And so we're going to talk about 3 issues of using regression models to solve this specific problem. The first is the performance of the model under conditions of data scarcity. The second is the dimensionality problem. And the third is this problem of inflexibility. And then I'll talk about in general how this is addressed by the new framework. So the first issue is that data scarcity is actually affecting the reliability of the estimates that we get from linear regression. So when you have very scarce data, the regression is actually just interpolating across those scarce data points. So this is going to cause bias or overfitting, usually overfitting, where the model is going to track too closely to the 3 data points that we have in 1240. And this means that our model is not going to be able to make a good prediction in a new setting. It's paying too much attention to the few data points that we have. And this is fortunately a problem that has a very clear solution in the predictive modeling literature. And so what we have to do is shift from thinking about regressions that use all of our data to thinking about a predictive modeling framework. So we're going to have this training data and this testing data, and then we're going to use that data to predict in a year outside of the training and the testing data. And so what this does is it avoids this problem of connecting the dots. And so instead of running a single regression line on all of our data, we'll make sure our model doesn't overfit. And we'll do this by measuring and optimizing on what's called out-of-sample accuracy. So this is the predictive power of our model on unseen data. And so this is going to help to ensure that our model is predicting values that are representative and generalizable, which is what we want, that single value of a wage for a country in a year. The second issue is often called the curse of dimensionality. So there are so many factors that affect a wage. You can probably think of some now. You might think of gender, the duration of the work contract, the place that the work is taking place, if it's rural or urban. And so what's happened since 2005 when these models were introduced is that good researchers have added more and more controls to these models. But data are scarce. And so as we add variables to the right-hand side of our regression, we start to encounter this problem of the curse of dimensionality. And so this is where we don't want the number of variables in our regression to be nearing the number of observations in our sample. And you might think, like, how would someone have 9,000 parameters in their regression? But this can easily be met if, for example, in the Clark regression, you're interacting a dummy variable for every single place that you have a wage observation with something that you want to vary geographically. And so this is another area where machine learning can really help us. So we're going to use algorithms that incorporate regularization and dimensionality reduction to basically directly affect this curse of dimensionality. And then we're also going to use the more recent data to predict the most historical data. And we're going to use the most observations of data to predict the furthest away data. And so this is giving us the most statistical power in the period that we have the most uncertainty. And so we're kind of forcing a larger sample when that prediction gets harder. And then the last issue here is the inflexibility. Least squares regression models are inherently inflexible. If we're building a model for 700 years, it's difficult to allow the impact of every factor to vary over time. So take the idea of having a variable that says if it's an urban or a rural wage. You can imagine this is something that's very important to control for. But if we just put that in one regression model for 700 years, we're assuming that the impact of that factor on the wage stays the same for 700 years. Now, if you've taken an econ class, you probably know there are 2 ways you could fix this. The first way is that you could allow this to vary in the single regression model by interacting it with lots of things in your regression, such as an indicator for every single year of your sample. But that's going to add 700 parameters to the regression you're trying to estimate, bringing us back to the curse of dimensionality and our problem of scarce data. Another option is that you could take your sample and you could say, okay, I'm going to estimate one model for the urban workers and one model for the rural workers. And this accomplishes our goal of allowing the differences to change and the way that that's interacting with other factors to change. But it's going to eliminate all spillover effects. And so we think that whatever is happening to rural wages also is impacting urban wages. And so we actually want these to be in the same model. And then you're also taking your sample and making it smaller when you do this because you have to subset it. So the fix is to use these flexible machine learning algorithms. And basically, these algorithms are going to experiment with these kind of higher order interactions to see what has the most predictive power. And we'll be able to use a single model and estimate different predictions for subgroups from the same model. The other thing that we're incorporating into this new method is a temporally sensitive framework. And so you'll see this in a second, but we're gonna basically use a slightly different model in every year, which allows all of our sort of parameters, the impact of all of these factors on the outcomes to change a lot over time. Okay, so what is the new framework? I am not going to go into too much technical detail here because I mainly want to help you build an intuitive understanding. So to remind you of our goals, we want a prediction of a sort of representative average wage for a country in a year. But we need this to come from scarce and fragmentary data, few observations taken from different sites for different types of workers. And now we're aware of all of these limitations of the standard regression approach. We need to make sure we're addressing those. And so the innovation of past predictive modeling is threefold. So first, instead of running a single regression on 700 years of data and interpolating, we're going to shift to this prediction framework. That's the first innovation. But then instead of predicting forward, which is like what the macroeconomists do at a central bank, where they're trying to predict what GDP will be in the next year, we're going to predict backwards in time. And the reason that this makes sense is when you're predicting to the forward, to the future, you're thinking about where you have the most uncertainty. We don't know what's going to happen in the future because it hasn't happened yet. When we're thinking about history, as we go further back in time, that's where we have the most uncertainty. And so that's where we need to be making kind of the predictions. And then we're going to use machine learning to generate these predictions, which is kind of like the third innovation here. Okay. So the key here is that we need to follow kind of the standard best practice predictive modeling techniques when doing this. And so that involves taking our 700 years of data and splitting it up into separate chunks. And the only difference is that each chunk is going to go further back in time. So we'll have this training sample, which is going to be the data that we use to estimate or train our model. And then separately, and for a year that's not included in the training sample, we'll have the validation sample. And this is where we're going to optimize how well our model is predicting the actual historical data in that validation sample to make those predictions as good as possible for unseen out-of-sample data. Then when we're happy with our model, we're going to use it to predict the values in the testing sample. And there we're going to measure our accuracy to see how well did we predict the historical data that we have from the testing year. And then finally, once we've trained, tested, and validated our model, we're ready to make a prediction. And so then we're going to make the prediction of the year just before the testing sample. And so you can kind of see here that this out-of-sample prediction is therefore being estimated 1 year at a time. So we have to basically resplit the sample this way 700 times. That's not a problem though, because we have like computers and yeah. And then it's important to kind of emphasize here that we're only ever using like original raw historical data collected by historians in archives, mainly my co-authors and not me. But this is all real data. And so we're not going to ever take our predictions and put them back into our model. This would be kind of like a recursive strategy. But we don't want to do that because we don't want to like kind of stack our errors on top of each other. You can imagine they'll get exponentially bad if we start plugging it back in. And then our accuracy, we're always measuring by kind of validating to this, the historical data that we do have. So for a given combination of traits, can we predict what the wage was in that validation and testing sample? So it's a little bit easier to visualize this. So to orient you here, the x-axis here is time, which is increasing as you go this way. And then looking at that top row, which says first iteration, we're going to use data from time t equals 7 to t equals 10 as our training data. Then we're going to optimize that model to make it perform well in unseen data using our validation data for t equals 5. Then we're going to see how well our model is working. Measuring our final measure of accuracy is going to come from the testing data in t equals 4. And then we're going to use that model that we're happy with to make the prediction for t equals 3. And so the first iteration, we get only a prediction for t equals 3. Then to get the prediction for t equals 2, we have to re-split the data. So in this case, we're going to use t equals 6 to 10 as our training data, t equals 4 as our validation data, t equals 3 as our testing data, and then we get the prediction for t equals 2. And so you can see how we're essentially running 700 iterations of this to get the prediction in every year. And in each iteration, we're using more and more data in the training data set. So this is called an expanding window, and it's a very common predictive modeling setup. But instead of expanding the window forward in time, starting from wherever your data begins, we're expanding backwards in time. So we're using incrementally more data the further back that we go. And so you can call this a walk backward expanding window, because in each iteration, we're walking backwards one step in time, and our size of the training data is growing. So this is the framework. And you might have noticed the last 3 slides, I haven't said anything really about machine learning algorithms. And that's because we set this up so that you could use any supervised machine learning algorithms. And so in the paper, we write this all up formally in a kind of general way. And so any algorithm that is going to map inputs to outputs, you can use to train the training data. And so in the paper, this is very far from what's been done before. And so we took the time to test 11 common machine learning algorithms. 3 gradient boosted decision trees, including XGBoost, LightGBM, and CatBoost. And these algorithms basically are creating an ensemble of decision trees and then iteratively boosting to make the model prediction performance as good as possible. And the reason that we use these is that they're known to be very good at prediction. Then we use 3 regularized linear models. So basically, we're adding that idea of regularization into linear models. And then we use 4 neural networks that just have a different number of hidden layers, but we also add regularization and ensemble techniques to try to address this sort of overfitting problem that we think is happening. And then all of these we're going to compare to benchmark linear regression. And so as I mentioned briefly earlier, Gregory Clark generously shared all of the underlying wage observations in his 2005 regression with us. And so we have all of this original data. And so the benchmark linear regression that we're going to compare to is one that we've kind of styled after this classic regression that's been used to generate the wage series that's kind of our standard wage series for England. And so the case study where we're going to be evaluating these algorithms is this English data for 700 years. And so when we test these strategies, this is what we find. Now, this isn't a key result. Don't take a picture of it. It's in an appendix, actually. But I thought you might be interested in it. So here, our y-axis is the out-of-sample prediction error, so the root mean squared error. And it's called error, which is a signal that we want lower is better. And so you can see I've put a box around these gradient boosted decision trees that are really doing a great job at prediction. And so this is not a surprise if you know machine learning, but the one that we're going to go for here is LightGBM. So now we can move to kind of the headline results. But before I do that, I want to remind you that our question has 2 parts. So first, does this methodological improvement make our prediction, now we know these are predictions of wages, is it making our prediction of this representative wage more accurate and precise? And we'll be comparing it to these standard regression methods. And then second, do these improvements lead to new historical knowledge? And so I should say on the first question, theoretically, based on everything we've learned, this should be true. But we're going to take the time to kind of rigorously test this because it's a new method. So starting with our first question, our new approach dramatically improves accuracy and reduces uncertainty. So the gray box here is that traditional linear regression that has been used to generate the long run series of wages. And our new estimates are this blue box. And so you can see on the right, our new estimates are reducing our standard errors by 60%. And so this is a huge, huge improvement. And so our estimates are a lot more precise. And that stability is really coming from addressing the overfitting problem. And so if you're interested in that, we talk about it a lot in the paper. And then as you could see kind of on the bar chart I just recently showed, these methods are more accurate. And so those wages that we estimate in with the historical data that we're cross-validating against, we're more often than a regression predicting a wage that's close to the true value. And so we have almost a 27% improvement in accuracy. And this is an underestimate, because to make this comparison, we actually have to put our linear regression into that predictive modeling framework. We can't compare it to the regression on 700 years. And so it's a pretty big effect to be an underestimate. When we dig into this a little more, we find that in every single year, our estimates are more precise. And so here we've separated out the laborers and the craftsmen, which is a common thing to do in economic history. Our laborers are like our unskilled workers, and our craftsmen are like our skilled workers. And the old estimate standard errors are in blue, and our new estimate is in orange. And you can see that our estimates are much lower in every single year. And these are bootstrapped standard errors. And these reduction in standard errors are actually greatest in the decades that have the smallest sample sizes. So we're getting an improvement in every single year, but we're especially getting an improvement where data are most scarce. So the y-axis here is the difference between the old and the new standard errors. And so our new standard errors are much lower than the old ones when the sample size is smaller. And again, I've separated laborers and craftsmen. So to summarize on our first question, yes, this seems like a big improvement. We have much more accurate and precise results in every single year. Our standard errors are lower, and it's doing what we think we do. These improvements are coming even more in the periods that have the most scarce data. So now that we kind of believe in this new method, we have to see what we can learn about it what we can learn from it for history. More accurate and precise measurements are good, but learning new methods is hard. And so we wanted to really ask if this was worth our time. And so we're going to talk about two examples here, the Black Death and regional wage series, and we have a few more in the paper. But before I do that, I just want to show you our new long-run series of wages that we get from this method. And again, I've separated the laborers from the craftsmen here, but these are estimated from the same model like we mentioned before, because that model is so flexible. And so there's two things to note about this, and these are real wages. There's two things to note about this. So first, this is the first long-run series for England that has any kind of confidence interval. So those regression methods, you can get a confidence interval out of it, but that was not a focus of the work back then. And so people download the existing wage series and they have no measure of uncertainty around it. And so we can give you this measure of uncertainty around the wage estimate. And then second, this series differs from our standard wage series by up to 10% in some decades. And so there are some decades where we're getting a pretty different wage than what's currently being used in a lot of economic history research, not just on England, but in a lot of those cross-national papers looking at the effect of the Black Death on labor markets. So to kind of show you these differences, we're going to zoom in now on the Black Death, which is a historical setting that has kind of scarce data. Why are we interested in the Black Death? This was the single largest labor market shock in history. And while it was a Europe-wide phenomenon, when it reached England in 1348, it killed between a third and a half of the population. And this has been a subject of a lot of work in economics and history and economic history, because it's an example of what we call a Malthusian shock. And so Thomas Malthus speculated that something like this that's going to decrease the population is going to increase living standards. And so we're interested in what happened to wages around the Black Death to see if living standards did increase. And we've had long run wage estimates, and so a lot of people have looked at this question. But what I want to show you is that our estimates are different than what we've had. So our new estimates are in orange, and the existing estimates here are in blue. And these are all in nominal terms. And the laborers are there on the right and the craftsmen on the left. So starting with the laborers, what we find is a more rapid, larger, and more sustained increase in wages after the Black Death, 1348. And so what I'm looking at here is that that orange line is consistently above the blue line. It's shooting up faster, and it's staying up there. And so we're finding a 70% increase in laborers' wages with the Black Death, and the previous estimates are only showing a 45% increase. And so we think laborers' wages grew more than we previously had thought. But for craftsmen, we see kind of a different story. So our predictions here are consistently lower than the existing series. And so this divergence shows us that the Black Death was skill differentiated. It impacted unskilled and skilled workers differently. So unskilled laborers that had these casual day work contracts, they had the option of doing agricultural work, they're benefiting the most from the shock. And for skilled workers, they are seeing a benefit, but their wages are much less responsive. And there are lots of historical explanations for this, such as Ordinance of Laborers in 1349. And so what this means, if you're an economist, is that the skill premium is much lower than we've previously been estimating. And so wages are going up for the unskilled workers more than for the skilled workers. And so the unskilled workers are seeing the benefit of that Malthusian shock. And so this means that the Black Death was inequality reducing in the wage labor force, making wages more equal between these two groups. But I want to show you that the contribution of this new method is not just in periods where data are scarce. And so these are another set of results. So this new method is going to allow us to generate the first consistent long-run series of regional wages for England. And you see them here for laborers and for craftsmen. And this ability to generate this long-run series of regional wages is coming from the flexibility of the machine learning models. And so we were talking about this problem before of, do you interact an indicator for regions? Do you estimate models separately? Here we can parsimoniously back these out from a single model to get a long run series. And this is important, first because it's new. We have nothing to compare it to here. But these kinds of graphs are important to help us understand the timing of key historical periods of economic development. So the first is this 16th and 17th century divergence of London from the rest of England. And this was driven by international and especially Atlantic trade. And you can see this really clear divergence of the London wages. And by 1650, wages were twice as high in London as they were in other regions. The second is this later 18th century process of convergence as productivity grew with the Industrial Revolution. And so we're kind of timing that convergence to around the 1770s. And so one contribution is that we have regional wages. Another thing that we do is that we're going to take these regional wages and we're going to weight them by population to create a more representative national average. And this is not an innovation. This is the best practice. It's what all of our standard statistical agencies do. But having the long run series allows us to do this in the long run. And so to our second question, while I've only covered in detail these two examples, we can see that there's historical benefit here. So our new series differs from the existing series by up to 10%. It's the first to have these measures of uncertainty. And when we look at the Black Death, we find that wage growth was higher for unskilled workers than we had previously thought, and lower for skilled workers, meaning it was more skill differentiated than we had thought. And so this is reducing inequality. And then we also saw how this method allows us to estimate long-run regional wages, timing these key periods of economic development. So to conclude, we talked about machine learning in all of its various forms and how it offers a tool. Oh, let me start. Take a step back. We started by talking about all the ways that we're concerned about AI, because I think it's important to kind of acknowledge what's on our mind to make us ready to learn something new. We've been told AI is going to make our lives better, but there's been these instances of these false promises where AI has had unintended or intended consequences that are leaving people feeling concerned. And so this causes us to kind of focus on this question of how can we use AI differently? Not to look forward, predicting what people will buy or trying to influence that, but to look backwards to help us do historical research. Uncovering these patterns in data at scale and also helping us to answer questions about the past that we couldn't before. And then we talked about machine learning, and hopefully I convinced you that machine learning is a really great tool to make predictions in these complicated and changing systems, and that in many cases it can improve on what we can get from a linear regression. And we talked about how, while it's been used for predictive analyses a lot in econ, in history so far, we've mainly used it to gather and process new data for data digitization, extracting data from new sources, using text as data, and linking records. And while all of this is very exciting, it's not fully utilizing the power of machine learning to help us with predictive analysis in history. And so then we talked about this example where my co-authors and I are trying to do that with past predictive modeling. And I showed you how when we replace a task that's traditionally been done with a linear regression with a machine learning algorithm and these kind of best practice predictive modeling techniques, we improve the accuracy and wages of our predictions, but we also learn new things about history. We're getting new insights on cases like the Black Death and these regional wage differentials. And these are things that traditional methods haven't been able to get and have been missed. And so, can we find a path forward of excitement? I just want to leave you with my observation that whether we're concerned about AI or excited about it has to do with who is using it and how. If we just leave AI and machine learning to all of these big tech corporations, these tools are going to be optimized to make money. And that might be at the expense of people and institutions that we care about, and that will leave us feeling concerned. But when we take the time to actually learn these new tools and harness the tools to augment our work on things that matter, like scholarship in history, we create reasons to be excited about AI. And as we do that, I want us to continue to push further, leveraging the predictive power. So not just using AI to get new data, that's not just what history is. We want to use AI to help us to analyze this data, to shape our analyses, and especially in cases where what we care about is making the best prediction of what happened in the past. Thanks.
Thank you, Meredith. I've got a small gift, so I'm going to say thank you.
Thank you.
But the one thing the LEAP lecture should do, or a keynote, is to make you want to write a lot of papers. And now I feel like I need to go and write a lot of papers. So thank you for that, although it's not as if my list is not long enough already. But it's really exciting. I think this is the kind of message that we want to be exposed to, that we want to expose our students to as well. And so I hope that many of them will also listen to the lecture online and be inspired by these tools. I should say that this is the 10th LEAP lecture. When I initially had this idea in 2015 we established LEAP, and in 2016 we had Marianne Wanamaker here as the first LEAP lecturer. I could never imagine that 10 years later we would still be going on. Of course, this is all thanks to the support of the department. We're based in the Department of Economics at Stellenbosch. But it's also because of people like you that join us here, our donors who really are fantastic and support us every year. So I want to also thank them. I want to thank you, and thank you for inspiring us to hopefully continue this for the next decade. Thanks a lot.
Thanks.
Thanks, everyone.